Hi everyone. So today I'm going to talk about the interstellar medium of galaxies through cosmic time with far-infrared emission light luminosities. So let's start with the interstellar medium or ISM, that is typically divided into different phases. Some of these phases are the cold, neutral, the warm ionized medium, the dense molecular clouds, and even the H2 regions. Each of these ISM phases is described by a range of temperatures and densities that allow us to trace them in some specific emission lines. For example, H alpha can be used to trace the warm ionized medium, and CO can help us to trace the molecular clouds. Although we know about these phases in the local universe, we want to know how the ISM evolves to understand its evolution with cosmic time. The problem is that we cannot resolve the ISM at cosmic noon, so we needed to infer it from integrated line emission. And some of these lines are essential and are helping us to obtain redshift, metallicities, and kinematics properties, among others. In the far infrared, we found several of these important lines, each of those tracing different ISM phases. A great example is the C plus luminosity that can be traced by different ISM phases. This line is very bright, and compared to others, it can help us to resolve 4 ISM phases. With the information that we can get from these lines, we ask two questions. The first question is how much luminosity comes from the ionized neutral molecular gas, and the second one is how coherent is the ISM physical conditions derived from these infrared lines in galaxies at different cosmic epochs. But how do we solve these two questions? Well, for this, we use a set of SPH cosmological simulation and we post-process them. In our case, we use the Eagle simulations. In these simulations, we need to make some assumptions to obtain the information of the SPH and create an ISM model. So for this ISM model, we use a computational tool for line excitation as cloudy, and we study the cold gas and how the incident radiation propagates inside the neutral cloud. These computations with cloudy were previously done taking into account different sets of grids in terms of redshift, temperature, metallicity, and gas density. These grids can be used to understand the gas properties in galaxy scale environments, such as the one that we have in Eagle. Then, our approach is to combine Eagle and cloudy to predict several emission lines, to then obtain some global properties of the galaxies through cosmic time, and finally compare it with some observational results. So one example of this is this graphical representation of a galaxy inside Eagle. This is only the information that we obtain from the gas particles that are creating this fuzzy galaxy. Then what we do is that we take that information and also information from the star particles to estimate some physical parameters as the local interstellar radiation field or the star formation rate density, to divide it into neutral gas, ionized gas, and then try to create a cloud structure taking into account these temperatures, density, and some radius in terms of the neutral clouds and the diffuse ionized medium, and then use that information inside the cloudy grids to divide the luminosity of the lines, in this case the C+, into the different phases, atomic, molecular, and ionized. Once we have this ISM model, what we do is to implement it inside Eagle, and the information that we get, for example, in this galaxy, as the one I showed you before, can help us to divide the phases into what is the diffuse ionized gas, the atomic gas, and finally the molecular gas inside the galaxy to create the total luminosity of the galaxy at the end for a given line. With this information, the first thing that we do is to try to make some predictions for the star formation rates and luminosity relations with the C++. So first, we know that the observed local galaxies follow a typical trend described by a power law uh, from 2014, and we compare this information with our simulated galaxies. So we do it with a small box, a small simulated box, then with a big box, and finally with a high resolution box. All this together show us that our predictions with our ISM model predict the same relation that we are seeing in the local universe with at around 6,000 galaxies, and that reproduce the average star-forming galaxies in this relation. But with this information, we can also get the fractional contribution of the ISM phases. So in C++, we are seeing that depending on the star formation rate, the fractional contribution of the different phases changes. For example, the diffuse ionized gas is a high contributor in low star formation environments, while the atomic and molecular gas are more important in high star formation environments. Compared with our Milky Way and some values from Pineda et al., we find that our estimations coincide to what we expect with a similar galaxy as the Milky Way. We also compared it in terms of metallicity, and we found that the diffuse ionized gas increases at high metallicity, something that was also found in observational results from Kroxat et al. And Cormier et al. In 2019. So these two things together are showing us that the ISM contribution on the C+ line depends mainly on the total star formation and metallicity, and it changes depending those values. Now, we are extending our model in terms of different redshifts, lines, and we are also adding H2 region as a new ISM phase. So now, our model looks pretty similar to the one that I showed you before, but now we are adding a new cloudy grid for H2 regions to predict the H2 luminosity that comes from very young stars in the ISM to finally obtain the line. Our predictions now goes up to redshift 6, so not only the local universe, and we focus on 8 far-infrared lines. The O1, O3, nitrogen 2, nitrogen 3, and C++, the one that we showed you before for the local universe. And we compare these estimations in terms of the physical parameters of star formation rate and a specific star formation rate, metallicity, the interstellar radiation field, density, and other masses. So our first result shows us that when we were comparing the luminosity of the C+ against the star formation rate as we did before, at different redshifts, we see that the observations follow the same similar trend that we see on redshift 0, and now with our simulations, we are reproducing the information that we get at different redshifts, especially at redshift 6 and redshift 5, but not so well at redshift 2 and 3. But C+ is not our only line. Here is an example of what the oxygen 3 looks like in our estimations compared with the few observations that we have and some other linear relations that have been derived from other models. So in this case, our simulations, the ones that are in cyan and olive, seems to show a typical trend that slightly evolves with redshifts. So from these results, we can see that at least our estimations with our ISM model seem to be coherent with different redshifts. Now, in terms of the different ISM phases and their contributions, we first observe the C plus line, and we obtain a similar result to what we had before for the local universe. But now, when we compare it to different redshifts, we observe that the atomic gas is the one that dominates in most of the cosmic time that we are observing here, with a high contribution of H2 regions at high star formation rates. In terms of the C plus, that's the result. But now we are observing the O3 as well. And in the O3, we see also an evolution of some of the ISM phases, but the balance between these phases, in this case the diffuse ionized gas and the H2 regions, is not so obvious as with the C+. And this is telling us that we can trace the evolution of the ISM phases through cosmic time and using different far-infrared emission lines. Finally, we compare our estimations in terms of diagnostic diagrams for the C+, O3, nitrogen 2, and oxygen 1 for the different cosmic times. And with this, we can see how they evolve and how do we expect that these values in these diagnostic diagrams change with respect of redshift. But not only that, with the information that we have, we can see how the different physical parameters affect the position of the galaxies in these diagnostic diagrams. As for example, we see with metallicity, where the C plus over O3 is a great metallicity indicator in a given range. And then the nitrogen 2 over oxygen 1 is even better at very low metallicities. So these results can tell us that some of these far-infrared ranges can be used to trace the metallicity and star formation rates, among other things, depending on the ratio that we were using. So in conclusion, and trying to solve our first questions on how much luminosity comes from the ionized, neutral, and molecular gas, first, we need to mention that we implement an ISM model together with Eagle and Cloudy, and we reproduce the luminosities of the different far-infrared emission lines. And it seems that the ISMs depend on the ISM on the lines depend on the star formation rates and metallicities of the galaxies. Trying to solve the second questions on how coherent are the ISM physical conditions derived from the infrared lines, we find that the results at different redshifts seems to agree with observations. And with some radius as the one of C plus and oxygen 3 and the nitrogen 2 over oxygen 1 that we show you here, it helps us to trace the metallicity and the specific star formation rate for the galaxies. As a future steps in our project, we want to see how these estimated line luminosities change depending on other global characteristics of the galaxies. And we are working on that at the moment. So thank you very much for listening. And if you have questions, you can contact me.